Yes, and to understand what is difficulty, I want to say that if you have, for example, three equations and three special variables, we obtain the matrix. Yes, I'm talking about computational with symbols, matrix containing symbols. So matrix with polynomial elements of 15 variables consisting from 400 to 450 monomials. So it's case of n equal to 3. And it's quite a problem to solve because the main idea of my work was to find in this matrix similar parts of these polynomials and try to reduce the form of that matrix, so I could compute the eigenvalues by some general procedures, something like this. And if you want to repeat all the actions I've done, here is algorithm in general form. So anyone can do this. And this is a computation summary. So I used such a computer. I think here on those 12 cores is just to show how good are our computers, because in Mathematica you have to write a parallel program to make it compute with all the scores. But the estimated times for these numbers of equations is like this. So I think with my current methods of simplifying this matrix, it's I think some limit, and I have to find some more extended algorithms to be able to reduce these polynomials in the matrix. So it's pretty all of my talk, and if you have some questions, I will be glad to answer them.
Thank you very much. Any questions or comments, please?
As far as I understand, from the very beginning, you said a lot of assumptions that we need some. I'm talking about just one assumption. You said that you don't want that eigenvalues have multiplicity more than 1, if I remember correctly.
Yes.
Yes. As far as I understand, in practical computations, not symbolic, but in numerical computation, it doesn't matter, because if we have multiplicity more than 1, we can just add some little and it doesn't matter. Is it important? Is this condition is really important for your case, or you can just
No, it's just for convenience of computations. Yes, it is already written that it doesn't affect the generality of our solution. So it's just to, for convenience.
Okay, thank you.
Any further questions or comments? Then I have a question. Please show me slide number 1, first slide. What about the matrix A on the right-hand side? are the entries of this matrix constant, or the functions of time or spatial variables? The entries, elements.
Yes, I understand. Well, do they depend on t? You
Yes,
mean?
on time or other independent variables.
Okay. Okay. My co-author, Andrei Nesterov.
And
no, in the initial work, the elements of the matrix A and D is a constant. Yes, but the algorithm may be extended to как переменные. Yes, to the variable elements of matrix A and matrix D. Yes.
in the mathematical literature, such terms are called source terms. Source. Источниковый член. Source. The right-hand side, like in your case. Source term. Maybe later. My second question is as follows. What do you think is this right-hand side the source of the burst which you study in your talk?
Source of
the burst phenomenon. Physically.
Yeah. Evgeny Vasilievich, thank you for the question. We agreed with Andrei that he will answer all the physical questions here, and I'll answer the question about computations.
Do you know the answer?
The source of initial condition.
No. The source of the burst.
Burst. Скачка.
Physically, the burst may be may appear from the in such phenomena. We have a local distribution or local вброс какого-нибудь вещества. Yes, a local injection of some substances in multi-phase media. For example, media may consist from the hard porous, then through this media some liquid may transport, and some, this is two media, hard and liquid. And in liquid, someone inject local initial condition. And then this local initial condition transport from such multimedial system, multi-phase system. Yes. And the first terms of parameter epsilon becomes when the exchange between phases more faster than transfer processes. Exchange between system, between phase, most faster than transport processes. And then the main terms, maybe show this the next, and then the main part of the asymptotic will the solution of the equation number 5, and this equation is parabolic.
Yes, parabolic. Thank you. Are there any further questions or comments? No questions, no comments. All are satisfied. Thank you once more for your very interesting talk. Now let us proceed to the next talk. It is entitled On Spectral Asymptotics of Quasi-Exactly Solvable Quartic Potential. The authors Boris Shapiro and Miloš Tatar. I'm sorry for that. I do not know who is the concrete speaker. Ah, you. Can you already? Can you already show your slides and start your talk? Oh.
I need to share
Yes.
my screen.
Yes, yes.
It says host disable participant screen sharing. So I need the permission to be able to share my screens, my screen.
Chairman. Он хочет быть председателем. Yes, yes. Okay.
So who is in charge of Zoom? So
Кто ответственный? Ну, включайте.
I need to share my screen. Now I can do this. Thank you. Very good.
Кто председатель экрана? Он спрашивает.
Now it works.
Okay,
Yes, thank you.
please start your presentation.
Sure. Okay. Yeah, so this is a physically motivated talk, and I'll try to present some theoretical and numerical results mostly. So, okay, so we learn in elementary class in the quantum mechanics that we can find, if we take a quadratic potential and try to solve Schrödinger equation with a quadratic potential, with the standard boundary conditions that our solutions should be decreasing at plus infinity and minus infinity, then we can find the spectrum completely and the eigenfunctions completely. The eigenfunctions would be the products of polynomial factors, Hermite polynomials, and the exponential factor, which is decreasing at plus and minus infinity. But such a situation where you can actually solve the Schrödinger equation explicitly, finding both eigenvalues and eigenfunctions using some kind of algebraic procedure is very, very seldom the case. Such situations are called exactly solvable. But as soon as we already take the quartic potential, which there are hundreds and hundreds of papers, typically it's impossible to find its spectrum explicitly in the eigenfunctions. But in the mid-90s, two Soviet physicists, Turbiner and Ushveridze, found specific type of potentials where part of spectra can be found explicitly by some kind of algebraic operations, and also part of the eigenfunctions. The original example was the so-called sextic potential, but then there were found even quartic potentials of with non-standard boundary conditions, where this can be still, you can find a part of the spectrum and a part of the eigenfunctions. Such potentials are called quasi-exactly solvable. Quasi standing for that you can only find explicitly a part of the spectrum. And and the basic example of this form, which was later found by famous American physicist Carl Bender in the 80s, and his co-author Bircher, is this quartic potential which you see in Formula 1, but with non-standard boundary conditions. You require that your solutions decrease along the real on the positive half-axis, and also along the ray with angle 20 degrees going to infinity. So if you know these words, this would not be a Hermitian potential, but it will be so-called PT symmetric. Okay. Now, if this parameter j here in Formula 1 would be a positive integer, which I'll denote by n+1, then this operator maps the space of quasi-polynomials of degree at most n to itself. So this exactly solvable part of the spectrum looks very quite similar to those in the case of quadratic oscillator. This is exponential prefactor, which comes out from the potential, and times a polynomial factor. And this polynomial has degree at most n. So in a sense, such an operator sends this finite dimensional space of quasi-polynomials of this form to itself. So we are talking about a finite dimensional linear operator, and we need to find its spectrum and eigenfunctions, and we can do this by using linear algebra. So this polynomial prefactor P actually solves the degenerate Horn equation, and I can skip a little bit of the details and jump immediately to the matrix representation. So what we're interested in is for a given integer n, we are interested in, we have a parameter a of our problem, which is an arbitrary complex number, and we're interested in finding the spectrum of the following n+1 times n+1 matrix. It has four diagonals, non-vanishing, one under diagonal, then the main diagonal is vanishing, and then the first upper diagonal has this parameter a, and then the second upper diagonal. So that's how explicitly this differential operator acts in the standard monomial basis of polynomials of degree n+1. Okay, now there are two questions which we'll be interested in. First of all, we want to find some interesting regime when we increase n, the size of the matrix, and also change our parameter a, in such a way that we'll have an interesting limit of the spectra of this sequence of matrices. And also there is a second question which we'll talk a little bit about, which is, say we fix the size n. For a typical complex number a, the spectrum of this matrix will be simple, n+1 simple eigenvalues, but there exist a finitely many points, a, in the complex plane, where the so-called level crossing happens. Level crossing in physics language is where you have multiple spectrum. And we'll be discussing how these points are arranged in the complex plane, and how can you describe the monodromy. So if you fix some loop going around some level crossing points, what happens, what kind of permutation the eigenvalues of this matrix will experience if you go around, a closed loop, which contains some number of level crossing points. Okay, so let me maybe start with describing the second part, which is numeric, the monodromy thing, but then I'll also talk a little bit about the spectral asymptotic as well. So, okay, let's see. So it turns out that for a given size n, but this is a numerical observation, this level crossing points form a very, very strange looking regular pattern shown on this figure, with dots marking the level crossing points. So this, they are arranged very nicely in triangular-like shape. So additionally, you can show that if your parameter A is a big positive number, then your spectrum of your highly non-Hermitian matrix, non-symmetric four-diagonal matrix will be real, all of it. So you can choose your base point somewhere here on the positive axis away from the level crossing points, and you can make some kind of loop and going around and come back. And you can ask what happens, what kind of permutation happens with your spectrum, because your spectrum is real, you can easily label the spectral points from left to right. And let me show you what numerics suggest. It's quite nice, I think. First of all, one can actually show that if you take a huge loop, you start over here and make a big loop which goes around all the level crossing point and come back, what happens would be that your spectrum will completely twist. The least point, the minimal point in your spectrum will change place with the maximal point, the second with the next maximum, and so on and so on. This is shown on this picture. So your spectrum will kind of rotate 180 degrees. So the minimal will become the maximal, and so on and so on. Okay, but this one can show theoretically. But now let me show you the results of the experiment, which we have checked up to n equals to 10. And this means that you have quite a few, about 55, exactly 55 branch points. So this is, here you see the case n equals to 4 shown. So here's your base point. This is the value of your parameter A, which is a big positive number for which your spectrum is all real. Now, to describe your monodromy, what happens with the spectrum, you have to choose a system of paths. You have to choose generators of the fundamental group of your complex plane punched at the level crossing points. And so what we did, it turns out that the answer seems to be numerically very nice with respect to this system of standard paths. If you, for example, choose, so your level crossing points are arranged, as I mentioned, into triangular shaped with rows and columns. So what we suggest, so if we pick, if I want to go to, for example, this level crossing point, what I do, I go up to this height, then I go to this crossing point, then I make a small loop around it, and I return back in the same manner, going back to my original base point B. And so for each level crossing point, you have a standard path. You go to its height, then you go horizontally to this point, make a little circle, and go back and come back. And numerically, it turns out very, very surprisingly simple answer. Namely, if you go to any point in the first row here, independently of which, what happens with the spectrum is that the first, the least, the minimal point, and the next eigenvalue will change places. 1, 2, it's denoted by 1, 2. 1 is exchanged with 2. Now, if you go to any point in the second row, the second and the third exchange places, 2 and 3. Then in the next row, 3 and 4. And finally, here in this case, so we have 5. So the matrix size is n equals to 4, which means that we have 5 by 5 matrices. The spectrum consists of 5 points, and we have, so those rows are in one-to-one correspondent with so-called simple permutations of the numbers 1, 2, 3, 4, and 5. And the same recipe works for numerically up to n equals to 10, and then it starts quite difficult to verify it further, because for n equals 10, so the number of, it becomes numerically unstable. It's difficult to verify. Okay, so we have a bunch of other conjectures about the structure of this set of level crossing points. Let me explain it to you. And there is a very completely non-understood relation of these branching points to the zeros of the so-called Yablonsky-Vorobyov polynomials. If you ever worked with Penlevé equations, you have probably seen them. Let me briefly recall what those are. And I'll show you again some surprising numerics. Really very surprising. Okay, so there are two natural regimes when you want to study your branching points. For one regime, you increase the size of the matrix. So for each size n, you can draw those level crossing points, and you can see what happens if n increases. And you don't do any scaling. And let me first explain what numerically seems to be the case if you do not apply any scaling. So these level crossing points, in principle, they will form a bigger and bigger triangle if you do not do any scaling. Okay, and the conjecture which I put here says that if you take these branching points, these level crossing points for 3 consecutive values of the size of the matrix, say size 101, 102, and 103, and put them together, what you'll see close to the origin would be extremely close to the vertices of a hexagonal matrix. Hexagonal lattice, I'm sorry. So for example, this is a part of the picture. So the different colors, blue, green, and red, will give you these level crossing points for size 15, 16, and 17. And close, you see that this is a finite portion of the plane. So the level crossing points will be spreading and forming kind of curvilinear triangle. But in this finite domain, in this finite square, they're approaching exactly the nodes of the hexagonal lattice. And this is quite a surprise. Well, there are some hints why this should happen, but at the moment, even the specialists in Penlevé, similar kind of things, do not have a clue why such a regular behavior should take place. And this is indeed, at least, well, it's a quite fascinating thing. Okay, but then there is a different way to scale things. When you can scale your triangles, so you have this level crossing points forming a triangular shape, which let me show you again, maybe this thing, let's see here. But you can scale them with increasing n such that they will, the vertices, these corners of this triangle will come, well, we'll say be placed at the roots, cubic roots of 1. And then you get the limiting triangular shape, which seems to be exactly the one appeared in papers on Penlevé 2, related with the so-called Yablonsky-Vorobyov polynomials. Let me briefly recall their definition and also tell you some numerical results quite surprising. Okay, so Yablonsky-Воробьев polynomials, they are defined recurrently, and in the following way, you set q0 equals to 1, q1 equals to t, and then for n bigger, strictly bigger than 1, you define the next one. They depend on variable t. You define the next one using this expression. It seems like that this is a rational function, but in fact, it's a polynomial of degree n plus 1, choose 2. So this is a sequence of polynomials of degree n plus 1, choose 2. So the degree grows quadratically with n, not linearly, but quadratically. And why are those important? They're important because if you ever heard about Penlevé equations, this is the second Penlevé equation. And it's very special rational solution of Penlevé equation, which play a fundamental role in many, many situations. They can be fairly explicitly expressed in terms of these Yablonsky-Воробьев polynomials. Yablonsky-Воробьев polynomials were first defined in the 50s. They have been around for about 70, maybe 60 to 70 years. And they have been studied numerically, theoretically, and so on, but there are still many open questions about it. And what is extremely surprising is for our physical model of this quasi-exactly solvable quartic, and those level crossing points, they seem to be numerically extremely close to the zeros of these polynomials qn plus 1. Let me show you. So they are not the same because we checked it numerically. Both of them are given by polynomials with integer coefficients, very big, but integer coefficients. They are not the same. They're not coinciding. And their zeros are growing with the same speed, but with different leading coefficients. The difference is some cubic root of 2 between the leading coefficients. But if you superimpose them after dividing by this cubic root of 2, you see, so here this is not the zeros of one polynomial, this is the zeros of two polynomials with the same n. One shown by these red hearts and the other by these blue dots. And here maybe, I'm sorry, but here you see a little bit better, but this fragment is below, unfortunately. So this is a blue root and a red root around here. And this is approximately the limiting shape of this curvilinear triangle, which you'll get after scaling. And it's a miracle for some reason why these two families of seemingly unrelated polynomials, which are not exactly the same, will have such an amazing coincidence of roots after one scaling by cubic root of 2. So we have some numerical information how the maximal difference between this one family of polynomials and the other family of polynomials, how it grows, it seems to have a finite limit. This triangular shape would be growing in the complex plane, but the maximal difference between the zeros of one family and the other family seems to be always bounded. We did these experiments up to n equals to about 60. So there are quite many points there. Oh, sorry, not 60, even 110 was our record was 110. And it seems to be still bounded by something like 0.3. Although, these maximal roots would be of this, the maximal absolute value would be the scale of 1,000,000. So it's really quite surprising. Okay. Yeah, so that it's here it gives some values for n from 10 to 40, and it's still for 40 you still don't even have 0.1. It's 0.7. It's monotonely increasing, but increasing very, very slowly. Okay, and now I still have some 5 minutes. Let me maybe go back and explain a little bit about the asymptotic of this matrix. Okay, so let me. So far I have been talking about level crossing points for a fixed size n. So these are the value of this complex parameter A, for which you have coinciding eigenvalues of this matrix depending on parameter A, and for a fixed given n. And how the spectrum changes when you go around some loops. Encircling some of these level crossing points. And now let me just say a couple of words about that. You can, on the other hand, do asymptotics in n. You can increase the size and adjust values of A appropriately with increasing increasing size, so that you can get some interesting limiting spectral behavior. Okay, one of the situation occurs if you, for example, take A equal to 0 for all values of n, and you can take a look what happens with the spectrum for if the parameter A equals to 0. And a similar behavior occurs if this limit A n divided by n to the power 2/3 would be 0. And what you get is that after appropriate scaling by this factor, your spectrum would be asymptotically lying at these 3 straight rays through the origin. With the density, you can calculate the density would be an analytic function, not algebraic, but analytic function. So this we can prove with a mathematical rigor. Now, there is another asymptotic regime where you allow the limit of an divided by n to the power 2/3 to be to have a finite limit complex number capital A. And then with the physics kind of rigor, we have to assume that certain things have to converge, and we cannot prove this so far strictly. Then we also can show that after a rescaling, you get a very nice spectral picture, depending on this complex number A, which is shown here. So there are typically two behaviors. If this complex number A is inside the domain, which you'll get inside this curvilinear triangle, which I was talking about before, curvilinear triangle which you obtain by scaling these level crossing points, then this the limit of your spectra of your matrices with increasing n will tend to a figure looking like this, with looking like a tripod, 3 segments starting from one and the same points. And if your A lies outside this curvilinear triangle, you'll get just one single curve, smooth curve, where the spectrum would be accumulating. And finally, the boundary of this triangle will consist of a picture like this, where, for example, this leg of this tripod will shrink and kind of be glued to. You'll get kind of a simple arc, but it will have a singularity here. Okay, I think I would stop here. And so we have experimented a lot with Mathematica, really used its options and its numerical capabilities quite a lot. And yeah, it's fairly challenging numerically problem, and it would be nice to understand many part pieces of this project more theoretically, of course. Thank you so much.
Thank you very much. Are there any questions or comments? Then I have two questions. Have you used at some stage of your research work the symbolic computations on computer?
Yeah, so of course, yeah, of course we did this because we needed this defining polynomial, which will tell us where the level crossing points are. And this has been done symbolically, of course. You need to calculate a certain resultant. And the numbers you get, you need to get the numbers explicitly as integers, of course. And we also tried, so we tried to use Macaulay at a certain point to do symbolic algebra, but this didn't give us too much because, yeah. So we did symbolic calculations when we wanted to calculate the discriminant. Yes. Mm-hmm.
Okay. I would like to share your observation. You have in your matrix, whose spectrum you study, many zero entries.
Sure.
So one could then try to obtain analytic expressions for all eigenvalues. Have you tried to do that? After that, you could theoretically obtain the data about level crossings and explain their regular structure of points. Have you made such attempts?
Definitely. But I mean, this has been done before us by Carl Bender, who is a very known expert, of course. But unfortunately, those polynomials, they do not satisfy any kind of natural recurrences, which you can, use then. They jump in degree, they are of degrees increasing like n plus 1 choose 2. You have to be very clever to fill the gaps. If there is at least no obvious recurrence way to obtain their properties. You can definitely calculate many of them in the beginning, but this to get the general formula for any n, I'm not sure that this is possible. This is definitely not done, and I'm not quite sure how to approach this thing.
Okay, thank you. Are there any further questions or comments? No questions? Then let us thank the speaker once more for his very interesting talk.
It's a pleasure.
Now we go over to the next talk in this session. The talk is entitled qFunctions, a Mathematica package for partition theory application and its future. The speaker is Ali Kemal Uncu.
Thank you. Thank you. It's great to be here, a part of PASC 2021. I hope you can all hear me. And yeah, if you cannot hear me or if there's something, please interrupt me. Yeah, this is about the Mathematica package I wrote in collaboration with Jakob Ablinger from RISC. And yeah, and it is future. So let me tell you directly what we're going to talk about. So we will first introduce what partitions are and the basics that we need. And then I will talk about what the qFunctions package does and what it includes at this time. And then I will briefly talk about its future and our future plans for that. So when I say partitions, I'm talking about integer partitions. So for me, an integer partition is a finite sequence of non-increasing positive integers. So it is a finite list that you can add up, and it adds up to a finite value. And so you can just organize these objects with respect to their size, with respect to their total value. So here are two examples of partitions. 511 is a partition that adds up to 7. It is a partition of 7. And the empty list is just the unique conventional partition of 0. So all of the things that I'm going to introduce about partitions, you can find it in George Andrews's encyclopedia, The Theory of Partitions. So these are combinatorial objects. They show up in many different fields. They appear in computer science. They appear in statistical mechanics. Everywhere you see integer partitions, in combinatorics, of course, as I'm talking about that. But we tend to not deal with them one by one. It is better to deal with them in bulk. And for that, we need to define what a generating function is. And that is just, given a sequence, you make a series, a formal power series, by putting that sequence indexed by q to the power n's. And that formal power series becomes the generating function of the sequence that you have. For our partitions, for partitions of integers, you can make this formal power series. You take the partitions, group them with respect to their sizes, take all of the partitions, group them with respect to their sizes, and that makes a list. So the coefficient becomes the number of partitions of that number that you see in the exponent. For 4, there are 5 partitions, where all the parts are 1, some parts are 1, 1 is 2, 1 is 1, the other one is 2, the other one is 3, there are 2 2s and 1 4. So there are 5 partitions of 4. So this makes a list. Of course, we don't want to just have a formal list. We would like to understand this as an algebraic object. And for that, we define the next thing, and that is the qFunctions symbols. This is the generalization of the normal factorials for integers. So when q goes to 1, if you divide it with one basic factor, this actually also goes to the normal factorial. So this is the generalization of the Pochhammer symbol. This is the qFunctions symbol. And it is given by this formal product. And again, if you need convergence, you can take this q to be size less than 1 and restrict yourself to the unit circle. But as a formal power series, this also works, that a q sub infinity is just a limit of that formal product. And if you see the same base so many times and say the same products, we tend to use this abbreviation that a1, a2, all the way to ak base q sub l is the product of products. Okay, and how does this help us? We were dealing with these lists, and we wanted to have an algebraic understanding of them. We defined these qFunctions symbols, and directly we see that 1 over, we see that we can interpret this 1 over q sub n as the generating function for the number of partitions, less or equal to n. So that list that we have is just that n going to infinity. It is the generating function for the number of partitions. If you take n to infinity, you would get that product. You would get that generating function. Similarly, if you don't have the reciprocal product, minus q sub n, that is interpreted as the generating function for number of partitions into distinct parts. So these products appear in the theory as the building blocks. And to give you one more example, if you were to have this reciprocal product, 1 over q to the power 2, q5 sub infinity, that would mean that you're starting with 2, and you are going in steps of 5. So this is the generating function for number of partitions, where the parts are all 2 modulo 5. So this was 1 modulo 1, so it was all the parts. This was 2 modulo 5 parts only. And yeah, with this definitions, and maybe one more with just the generalization of the q binomial, we have the generalization of the binomial coefficients. We have the q binomial coefficients, which can also be interpreted as a generating function. We can define many different types of partitions, and we can write their generating functions. We can just write them as analytically or algebraically, however you would like to see it. And with that, we can now attempt partition identities. And for me, a partition identity is having two different sets of partitions that are equinumerous. So if you find two different sets of partitions where for each and every size, you get the same number of partitions, that means that you found a partition identity. So here's the first example. Here's the most famous example. The number of partitions of any integer n into distinct parts is the same as the number of partitions of n into odd parts. Thus, you're partitioning the same number into two different classes, and they have the same number. Here's the example. For n is equal to 6, you have these partitions being partitions of 6 into distinct parts, and these partitions are the partitions of 6 into odd parts. And these two sets are not the same, but they have the same number of elements. So this is a partition identity. We can see it combinatorially as we do here, or we can see it as a generating function level. So on the left, you have the generating function for the partitions into distinct parts. On the right, you have the generating function for the partitions into odd parts. And most likely, and this is just one special example that we see product is equal to a product, but most likely you would see that a sum is equal to a product. And there is a common theme in theory of partitions, that you have a sum identity which can be interpreted as a generating function, a sum being equal to a product which can also be interpreted as a generating function. Sums are usually difference conditions and products are congruence conditions. So odd parts is 1 modulo 2 parts. The most famous example here, and that I will just skim through right away, is the Rogers-Ramanujan identities. So you have partitions into non-consecutive parts, so the gaps between parts are at least 2. You count those partitions of any number that you like. That is equal to counting partitions with plus or minus 1 or plus or minus 2 modulo 5 parts. So you have this sum, which is actually, if you look at these summands, they are holonomic sequences, they're recurrent functions. This sum is equal to a product. And these type of identities are of interest. So being able to factor a huge sum, a huge series, is of interest for number theory, for combinatorics, for many other fields. But this equality is not easy to achieve. And that is the point where we need a lot of different techniques, and there is no unified technique. One main theme is these things are holonomic, these summands are recurrent, so maybe we can try to do something with them. And that is where qFunctions package comes into play. So the qFunctions package itself is a free-to-use Mathematica package distributed from the Research Institute for Symbolic Computation. Here's the website. You can just Google it, and you can download it and start using it today. And it is just to bridge the gap between the techniques of the partition theory with the implementations of the Research Institute for Symbolic Computation, or with other implementations that appears in Mathematica to solve things symbolically. And here is the published paper about the usage notes of this. So between me and, yeah, there shouldn't be an N, but yeah, me and Jakob Ablinger. Okay, so RISC already had so many packages that can prove things, which involves combinatorial objects like q-binomials, like q-polynomials, or the normal polynomials and binomials. But the partition theory techniques were sometimes just out there. We didn't have a way of carrying them to symbolic computation tools, so we decided to just build this frame, the qFunctions package, to take the partition theory problems, partition theory techniques, and carry them to the symbolic computation side, just to see if we can solve them on the symbolic computation side. All right, so there are 4 themes in this. We will talk about the q-difference equations, then a combinatorial technique, weighted words, cylindric partitions, another combinatorial technique, and a polynomial fitting. And I should say that this package has both symbolic tools and experimental tools. Yeah, so the q-difference equation, it is just you take your generating function, which might be bivariate now. So there's a q series, you add another variable on top of it. So you have a bivariate generating function. Maybe you can find what this function satisfies by just shifting y to q to the power i's. And here for the Rogers-Ramanujan example, you can see that it satisfies such a linear q-difference equation. And Such a Q-difference equation would mean a recurrence for this summand 2. We should note that. So you can go from the Q-difference equation to the summand, from the summand recurrence to the Q-difference equation, and you can try to understand this object better. And if you can factor this Q-difference equation, maybe you can even show that this is a product. So here it was a register margin example, and y to the n that we tagged along was actually the number of parts in the partition. The Q-difference, the qFunctions package has a guessing option for any Q-difference equation. So you can start with a sum, you can take along any variable that you like, you can take along up to 3 actually right now, and you can just say, can you find a Q-difference equation for me in these boundaries that I set? So register margin is a really simple example. I would like to move to the next example and show you how that in action too. So the next example I would say is the Caporelli's theorems, where a double sum is equal to a product or a sum of double sums is equal to a product. These were identified. The theorem is from 90s. The original theorem is from 90s, but it's the combinatorial version. The generating function, this analytic equality version, has been found recently. In 2018, Shashank Kanada and Matthew Russell found these sum sites by experimentation. And me and my former advisor, Alexander Markovich, were the first ones to be able to directly prove these identities. And the way that we prove them is what happened next. It's the Q-difference equations to say. So we can, again, just as in the register margin case, we can try to take along a new variable on the sum side and try to guess a Q-difference equation, try to find a relation that it satisfies. And here I'm just putting y to the power 2n plus m. Combinatorially, this is a natural statistic. It is the number of parts, again, just as in the register margin case. But for the Caporelli's example, if you do that, you would fail. There would be a Q-difference equation, but the order of that is not so low for the number of parts. But guessing is really important for us, because with the guess, you can just change the statistic and see if you have a better statistic that you might not combinatorially understand that would give you a good Q-difference equation. And that is actually what we did. So here I'm jumping to Mathematica, and I'm just doing the initiation. I loaded my qFunctions package. I loaded 2 more functions, 2 more packages from RISC. One is holonomic functions from Christoph Kuchan, and the other is sigma from Carsten Schneider. And the Q-difference equations example, I would like to show you this. This is the same series. It is a summand. I'm saying that, look at this statistic, x to the power 2n plus m, as in the example in the slide, and sum them up all the way to 20s, and try to find the Q-shift equation of order 3. Can we find it with the natural statistic? I'm doing them in real time on my laptop right now. And most likely, no. But if you were to go to another statistic, which is not so natural, 3n plus m, whatever that might mean, then you actually see that you can guess a Q-difference equation. And going from the Q-difference equations, you can, as I said, it's equivalent with the recurrences for the summand. So you can go to recurrences, this is symbolically, and you see that this recurrence equation, this Q-difference equation is equal to a degree 3 recurrence. But there is a trick in partition theory here, and we want to automate this in the future, that if you see a simple substitution maybe in the Q-difference equation case or in the Q-recurrence case, you can do that in the Q-difference equation case this time. You can clear the denominators and look at your recurrence again and lower the recurrence order. So I did one substitution that I'm not going to explain how I chose. I cleared the Q-difference equation a little bit, and then when I look at the Q recurrence again for the summand, from the order 3 recurrence, I now drop to an order 2 recurrence. And this trick can be played back and forth. So now you can go back to the recurrence, do a substitution, go back to the Q-difference equations, and do this trick to lower the degrees. This is something that we can automate, and that is one of the goals for the future. Okay, so yeah, there is this guessing function. Once you guess something good, there is the RISC packages to prove them. And that is why I'm sticking with guessing for this package itself. The next thing that is in this package is a combinatorial technique that is coming from early 90s. And this is all about handling these difference conditions on partitions in an abstract way and trying to get the congruence conditions, the other side of the partition identity, through this abstract gap conditions by substitutions. And Alari and Gordon came up with this technique, and in their technique, they were using this abstract gap condition and then guessing the generating function, which is a really hard thing to do. Then later, recently, Jaime Gutierrez actually came up with a technique where you don't need to guess the generating functions, but you can actually move to the recurrences again. You can go to the holonomic world, and then we can deal with these things. And we have actually implemented this method of weighted verse that was revisited by Jaime Gutierrez. So let me explain the system really quickly. You start with an alphabet with some order. So it makes your numbers colored. So you have the first A, the first B, the first C, the second A, the second B, the second C. And then once you have this list, it is identical with just having the normal natural numbers. You start putting conditions on them, the gap conditions, just as we saw in the Euler's theorem or Raj-Samajan. You say something like, I don't want B and AN to come together. So I don't want B2 and A2 to be in the same partition together, but B2 and A1 is okay for me. So a gap between B2 and A1, a gap of 3 is okay, but B2 to A2, maybe not so okay for me. And this generates a rule set, which you can create a gap matrix from. So going from A to A, you need one gap. Going from A to B, you need one gap, so on and so forth. So you can create a gap matrix and then move to this holonomic functions, move to these recurrences. And yeah, these generating functions satisfy some sort of a recurrence, and we have this in qFunctions package. So if you look at the weighted verse, if you take your matrix, give the names A, B, C as the colors, and generating function to be Gn, you can directly just ask what the recurrences are supposed to be. It says this generating function for A turns into these two, that generating function satisfies that recurrence, so on and so forth. And the way that I tackle this is different than Jaime Gutierrez's technique now. I want to stay in symbolic computation tools. We can use graphical basis and just uncouple these recurrences. And you can uncouple these recurrences using holonomic function spectra of Christoph Kuchman or any other picture that you like. And once you uncouple these recurrences, maybe you can even solve them. You see, one of these recurrences is actually of order 1, just C of n and C of n plus 1. And if you can solve them, which can be done by Sigma package by Carsten Schneider automatically, or you can do them by hand, you can get partition terms for free. I started with gap conditions. I ended up with products which are identical with congruence conditions. So I started with gap conditions. I got congruence conditions. I came up with just maybe a new partition theorem. And one thing to say, if your matrix is not good, if there are clashing rules that is coming from your matrix, our implementation can also find that it always terminates. So you never run into an infinite loop and generate infinite order recurrences. Okay. And the cylindric partitions, I think I will go even faster. So it is multidimensional partitions of partitions. There's a big rule. It is defined by Ira Gessel and Christian Kraptaler. Cylindric partitions is you put a partition on a cylinder and every order relation fits. The good thing is I was saying that going from the sum side to the product was hard. But in this example, Borodin actually gave freely from representation theory that we will always have a product side. He proved that for these cylindric partitions, we will always have the product side. So we need to guess the sum side, and that is all we need. And there has been a lot of work done by me, Cortil and Deus, by Cortil and Thomas Welsh, and recently by Ole Warnar. So we can actually try to solve this recurrence. Again, this is just a guessing scheme. And we know that we get the product for free. So you can look at this, after this substitution, you can look at this recurrence, which is also in the qFunctions package, and some more is going to be added soon. We are looking at symmetric cases of these cylindric partitions now. And with that, you can find these type of new partition identities. So here's one term that we needed to get this identity. So here's a fourfold sum is equal to the borrowed-in product, or you can simplify it and get this fourfold sum apparently factors, and it's a really nice product. And that is, again, in the cylindric partitions. It is, you start with whatever that profile might mean. You get your coupled system of Q difference equations. You move from the Q difference equations to their coefficients. So you get the coupled system of recurrences. You uncouple the system. I'm doing the same technique. So you uncouple the system. You see there are 3 recurrences. You take one of them. I'm taking the first one here. Try to solve it. Carson's package says that I have no solution for you. I have one particular solution, and that is 0. Then, so the solution is not easy. Then you start massaging this and try to see what you can do. So you look at your terms, which you can generate by the qFunctions package. So the initial terms look like that. You see that you can clear the denominators. The term seems to be recognizable. If you clear the denominators, you get a polynomial sequence. And if you want, you can guess a recurrence for them. And here's a nice recurrence for that. And then try to solve this one. And once you solve it, you get that product identity. But even more, if you have a polynomial sequence, just as in here, you can actually take your polynomial sequence and say, oh, maybe I can just try to write it as a sum, one-fold sum with known functions. And can I do that? And in some cases, you can just say, yeah, maybe I can. So we have this fit Q representation function in qFunctions. It is experimental. It has a library of functions, Q binomials, Q trinomials, Q Tn trinomials, the reflections of them. And given a polynomial sequence, it generates an undetermined coefficient system, makes a big ansatz, and tries to solve it. And whenever you see the solution is quite nice, maybe you can formulate it, and once you formulate that, you can go back to the RISC packages to prove them automatically. And here, we have this identity that we got using the Hirschhorn's recurrence relation. 3 of those sums were coming from the Hirschhorn's recurrence that was in the literature. But now we also saw that if you drop this n and look at that threefold sum, maybe you can even write it in a different way. And it gave us a new identity. A sum is equal to a sum transformation. A threefold sum is equal to a sum of 2 bilateral sums type transformation. And yeah, we can easily prove that using the other symbolic computation tools, as I was saying. So this is what the qFunctions package can do at this time, but we want to do more. We want to add more, and there's going to be a project related to this, so we will be working on this. So the first thing to do is to automate this degree lowering substitution. As I was doing, you go from Q difference, you do a substitution, recurrence drops a degree. You go from recurrence, you do a substitution, Q difference drops a degree. Not all the time, but we can automate that. We should find how to best do that and when to terminate. The second thing is extend the method of weighted versus domain. So we should be able to weaken the conditions to the point where we have multiple layers of matrices, and maybe we can even go from the normal difference conditions to the cylindric partitions. And the second thing is, the third thing is, as I was saying, the Q polynomial fitting is only dealing with single-fold sums, maybe bilateral, but single-fold sums. So maybe we should find a heuristic way of guessing multi-sum polynomial fitting functions. And there's some work on that. One possibility is to translate an equivalent version of the qFunctions to Maple, because the only reason why we wrote it in Mathematica was that tradition, those that Risk writes a lot of packages in Mathematica, and we knew some of these functions over there. And with the involvement of me with the with my involvement in the DuCat project and the CAD, maybe we can do more than just the partition identities. Maybe we can even do inequalities. And here is a new conjecture, for example, and there are many of them that we have seen. There are easier ones, of course. This one looks a little messy, but it says that this sum, which is a finite sum, has non-negative coefficient. This is an infinite series written as a finite sum, but we don't know how to prove it at this time. Maybe there's a way of writing these sequence elements, writing these summands as recurrence relations, and then use techniques to get their positivity using some sort of CAD or related technique. So there's much more to do, and hopefully we will be able to do that. Hopefully I will be able to work on this and get more results. Yeah, with that, I would like to thank you. And, yeah.
Thank you very much.
Not a problem.
Are there any questions, please?
Thank you for the outstanding talk, but my question about, have you ever seen a familiar theory about vector partitions? Thank you.
When you say vector partitions, do you mean plane partitions or just in general any vector partitions?
When we have to represent some vector as a linear combination of a set of vectors. This is vector partition.
So I have a feeling one of these special cases appear in the cylindric partition scheme, where we have partitions of partitions, right? So when we have a vector of the partitions, when it comes to full generality, we do not have it, but there are specific cases of vector partitions where we know we will get identities, and that is where I actually focused my efforts before. Yeah, so I would say in general, no, but some specific cases, yes, we have seen vector partitions. One of them is the cylindric partitions here.
Thank you.
Any further comments or questions? Then I have my positive comment. I am a chair of this session. I find your talk very informative because it contains all necessary definitions, and what is especially valuable for practitioners, it presents many application examples. Thank you once more for your very interesting talk.
Thank you. Thank you. Thank you for having me.
Now we go to over to the next talk. The next talk is entitled Computing Small Roots of the Polynomials Arising from Elliptic Curve Group Operation. The speaker is Jaime Gutierrez.
Good morning. Can you hear me? Oh. Okay.
Yes.
So my name is
okay.
Jaime Gutierrez. I'm from University of Cantabria in Santander, Spain. The local time here is 3 p.m. in fact, and we have a sunny day. So this is not the usual weather here in Santander. Anyway, here is the title of my talk, Computing Small Roots of the Polynomial Arising from Elliptic Curve Group Operation. And here is the plan of my talk. So I'm going to introduce this computational problem of computing small roots of polynomials. Then, the main tool to solving that problem is lattices. So I will provide you a short overview about the two computational problems related to lattices. But the motivation came from cryptography, in particular attacking the nodes in a pseudorandom number generator defined by elliptic arcs. Then I will come in the problem, straight to the art, solving the problem with some algorithms. Finally, I would like to show you the performance of my sixth implementation of the previous algorithms. Okay, so let's start. So, well, the problem is a particular case of the following well-known computational problem. So we start with n polynomial, reducible polynomial, n variable over the integer coefficient. And let me assume that they are reducible. We had, for practical application, we don't need this reducibility. But anyway, I'm having a common root. And well, we are looking for a small root in the sense that its coordinated are bounded by a certain known delta. And we need to bound this delta, for instance, like n forward to sigma, in order to recover the root in polynomial time. So the goal is to get sigma as much large as possible, recording the root in polynomial time. So this is the computational problem. That's the meaning of small, because they are bounded by a certain constant delta. We are looking for a root modulo a certain non-integer number n. So the case, for the polynomial one is for polynomial one variable, very famous algorithm with Governor's mean is provide an algorithm. Sigma is 1 over 3. There are algorithms, there are classices, different methods, with polynomial variables and several variables. However, in the general case, only heuristic results are none, the so-called Governor's mean. The problem has some applications to cryptography. Let me show you to illustrate one of the applications, which is by the way very well known, is the integer factorization. You know the factorization, the integer factorization is a difficult problem from a rational point of view. So we start with n. We know that n is the product of two primes, p and q. Well, we are looking for p and q. What is this? So what happens if you some information about one of the factors? For instance, if you know the most significant bits of p times p is equal n. And then, with this extra information, are you able to complete the operation of the bits? And the answer is yes, if if the approximation is good enough. But this is one of the consequences of this kind of methods. In any case, all of them are basic of the so-called vacuum reduction. That's the reason that I would like to give you a short overview about this technique. So a lattice, a lattice is a grid, a grid, in the plan, something like that. There is no the lines, but the intersection of the lines. The plane, of course, is a very well-known mathematical definition. So we have started with an independent vector. We need to know it R to the n, and consider the integer relation. The integer coefficient, the combination, the integer combination of the vector b1 to bn, not the left. It's a very simple definition. Here is an example. We say that b1 bn is a basis, so we consider the combination, the integer combination, and b1 bn is a basis. There are other bases, for instance. This is the integer flat. Here is one of the bases. The basis is one, well, that's much better. This is nice and much better. Okay? On the other hand, if we take two linear independent vectors, like one, and then we consider the linear combination, the integer linear combination, obviously, in general, you cannot get all the
Excuse me, Chaim.
Yes.
Unfortunately, the sound that we have here is very poor. Could you please try to move your microphone a bit further away from the headset or from the speaker or whatever? Because it's difficult to understand, unfortunately.
I see, I understand.
Yes, maybe a bit louder and a bit further away with the microphone from the headset, please.
So, what about this? It's okay now? Do you hear me now?
Yes, we do, but not that well, actually.
Oh, really? Oh. So, this is
There's maybe some problem with the microphone. Hello? Haim? Yes, now we don't have any sound at all.
Now?
Well, okay, yes, please proceed.
Oh, so sorry, I mean, maybe I can change the computer. Maybe here we have no one. But, I check it, doing it works.
Haim?
What about now? It's better? Or
Yes, now much better, thanks.
Great. Okay, so let me to continue over here. So this is of course this is a classical theory, That's a classical theory, in mathematics, which is called geometry of numbers. These people, these famous mathematicians, they have been working on this now. Okay, so there are two. The volume of the lattice provide, because the lattice are discrete side loops. That's the reason that always there is a non-zero vector with minimal node. This node, which is denoted by lambda 1, is called the first minimum of Minkowski, and the volume of the lattice provide a bound, okay, for this vector, and of course, I mean this is called the Minkowski bound. I mean the Minkowski bound, thing. I mean it's interesting to find, given a basis. It's interesting to find a vector with minimal node, which is called the sorted vector problem. And there are several indications that this problem is an NP-hard problem. Okay. So, however, I mean, also a similar problem, which is the closest vector problem. So we take any vector T, leading, in the finger space R to the n, and we are looking for a vector in the lattice with minimal node. This is called the closest vector problem, and this is an NP-hard problem. However, if we fix the dimension, both problems can be computed in polynomial time in the bit size of the coefficient of the basis, and also the number, because n is fixed. For say a weaker tax, I mean, we are looking for not the shortest, but short. A very famous, paper, the Lenstra provide, this short vector with a lot of applications. Okay, so in fact, our lattice consists of integer solution of a system of congruencies modulo of some positive integer q1 to qm, and typically the volume of this lattice is the product of the modulos. And the shortest vector and the closest vector are polynomial, can be computed in polynomial time in the bit size of the volume. Okay, so the motivation of the problem is, as I said before, is related to attacking, the certain linear pseudorandom number generator. This is a very well-known string cipher. And this very well-known string cipher satisfies the perfect secure if and only if, the key has the same size of the message from any new message, any new key, and keys are random bits of the same size of n. And of course, I mean, we can say that the producing random bits from the physical point of view is not efficient at all. That's the reason that we use pseudo-random number bit generator. Which is a pseudo-random number bit generator? Well, it's a deterministic algorithm that is starting with a value which is a random value, which is called a seed, produce some values that looks, we can say, looks random. And of course, that pseudo-random number generator, they have many applications, no, to simulation, but also to cryptography. So they should have very good statistical property, but from the cryptography point of view, they also has an extra property, which is about the predictability. In this sense, the linear congruential generator is not secure. It can be not used as a string cipher. Well, an alternative, a very attractive alternative, is the linear generator on elliptic R. Well, here we start with a prime P. We consider an elliptic R defined about this final field. This is in the Weierstrass form. Okay, we take a random point of the car. This is the seed. U0, and also we meet another parameter G, which is another point of the elliptic R E. So using this relation, we produce random number. Okay, we produce random number, and then, well, let me show you a simple sample. Now, this is a toy sample. Yeah, let me say that the period of these sequences is the order of the composer. In this case, in this particular case, this point of this elliptic curve over this field. Okay, which has, this elliptic curve has 35 points, and this is, the linear generator in this situation. So, well, this is our generator that we would like to attack. But first of all, I would like to introduce a new concept. So it's the concept of cryptographically secure generator. Basically, a cryptographic random bit generator is cryptographically secure if we cannot predict, the next significant bits if you have every information about the pseudo-random number. So in the cryptography setting, the initial value is 0, in this sense, and also the constants G, the composer, and the parameters in B are secret. And we output, the generator, and we output the sequences as a string cipher. Of course, if two consecutive terms are known, then it's easier to recover the set, and then to break the crystal system. So that's the reason that we output the most significant bits, in the hope that the rest of the bits should be more difficult to predict. Okay, here is the situation. Yeah, this is the motivation, and then let's do. Now I'm going to relate, this attack with the previous problem of computing small rods. So, well, we have a prime P, and we can represent the elements of the final field at P as integers between the range 0, P minus 1. Because, well, we assume that P is large enough, okay? And then let me assume the following, okay? The prime P and the composer G are known by the attacker. Which, of course, this is a very optimistic setting, but suppose that. However, no, the elliptic curve is a noun. Okay. Now, I provide you two delta approximations, and then we'll explain what the meaning of delta approximation. W0, W1, two consecutive values. We can assume that the consecutive values are the seed and the next one, and the U1. So at that approximation, you know, this is a pair that's known, okay? Two, you know, this is points, integers, such that, you know, this is the root that we are looking for, okay? The C, okay? Well, when I is equal 0 and y is equal 0, and this is known, and this is a noun, as is a noun, and also this is a noun, as our nouns in this case, okay? Because we are looking for something with a small, and the small now is because we have an approximation. That is, we have alpha I and beta I as you know, as input. And hello, yeah, okay. And then delta is assumed to not be independent of p. And the graph, you know, as large as possible, because sigma correspond to the less significant bits of the terms output of the sequence that remain hidden. And the problem is, with this extra information, with this information, could you recover in the C? Well, of course, I mean, depends, no? Depends on sigma. Depends on sigma. Okay, so sigma 0, or sigma 1, I mean, sigma is something small, probably you can, or it's something fixed. So, well, and then let me to, oh, okay, yeah, here, okay. So let me now to come and show the results, no, that provide, you know, solution of this, no. So an algorithm is presented, you know, with for delta smaller than p to sigma, with sigma is 1/6. It's a deterministic polynomial chain, and the lattice used in this attack has dimension 8. I mean, it's very small. It's more recently, you know, in 2020, you know, a better result is presented. You know, with delta, you know, because sigma is bigger than that. I mean, 1/5 is bigger than 1/6, so it's better result. However, it's heuristical. From the cryptographic point of view, heuristical, well, doesn't matter. The problem is, I mean, the question is if it works. If it works, that's fine, okay? However, there is a handicap, and this handicap is because, I mean, this kind of Cooper-Smith methods, from the theoretical point of view, is good, but from the practical point of view, they are very bad. You know, because the large lattice dimension, in this particular case, for instance, with sigma is 0.18, which is obviously smaller than 1/5, it requires, you know, a lattice of dimension 102. But not only that, the reason that if you really want to check your method, you have to check for, you know, for primes with, you know, with very big, the size of the price very big. Otherwise, I mean, you cannot get nothing interesting. So there are two handicaps, okay? Well, it's okay to come from the theoretical point of view, but from practical point of view, from real attack, though there are some handicaps. So the first thing that we can do is, you know, to show, to prove that there is a method, deterministic, with the same bound, the same, you know, threshold, 1/6. I mean, the same that it is 1, but using a lattice dimension of degree 5, or a lattice dimension 5 instead of 5. This is the first thing that we can do. Okay, let me to show you a method of sketch. So for this equation, which is the relation, okay, and assuming that, we get, you know, two polynomials. Now, two polynomials L1, L2 correspond, you know, to the coordinates, you know, to the two coordinates. This is the axis, and this is the ordinates of the point U1, which is a point of the elliptic curve. So in the previous paper in 2007, we applied the errors in the two equations, L1, L2, and we got a lattice of dimension 8. But in this case, we apply only, the equation in the polynomial 2, this polynomial. Okay? So remember that we are looking, for the errors, E0, E1, F0, F1, which are relatively small. Okay, this is our small group. So this is the first step of the algorithm. Then find the small integer solution, that is the closure vector problem. Check if the solution is correct. If not, compute the cardinality of the but say, oh, it's not correct. Why? And then we control the set of the points, the set of the value that it doesn't work. Okay, so let's follow. Okay, so then we get this vector. No, this vector contains, the errors, the noise, we can say. Okay, E0, F0, E1, F1. And it's a solution of the following linear system of congruences. I mean, it's a toy linear system of congruences. I mean, in the sense that it has dimension 5. Okay, and the coefficients are known because the coefficient of this beta 1, alpha 0. I mean, everything. This is the composer. Okay, the axis of the composer. So capital B's I are known, and then this is a linear system equation. Congruential linear system equation. So then we consider the associated lattice. I mean, just homogeneous, the previous system of congruencies. And then, well, we compute a solution of the previous system of congruencies using, any linearly Fantine equation, like, the Hermite forms. Then applying the algorithm to the closure vector problem, and for the vector t that we are computed previously, or this lattice. Well, maybe it happened that E is equal the E is the vector that we are looking for because contain the errors, contain the root. Then maybe is the vector B is known because it's computed previously. T is the solution of the system of congruences, maybe are the same. And now, I mean, the E is relatively a short vector because, okay. So we bound, no, it's not the case. Okay, we bound the possibility for which this process doesn't work. And then we obtain that the bound of this stat set has the cardinality of the order delta to the system. And that's the reason that we get, bound threshold that sigma is 1/6. Okay, but anyway, we can get a result in the following set. Suppose that we have more approximation. From the cryptography point of view, to have more approximation is okay. I mean, because in the sense that the problem is that good approximation. But to have many or more than 2, I mean, this is quite reasonable. Other story is that those approximations are good. I mean, the sense, are very close to the solution. But now suppose that we have k consecutive delta approximation to k points of our elliptic curve. Then there is some integers, okay? And then we are looking, and then so this is the information. This is the information that we know, okay? And then we are looking, for this small solution. And then, well, let me say that we can compute, but now it's not rigorously. We cannot provide, a deterministic polynomial chain, but we provide, a heuristic algorithm that we can recover in the C in polynomial chain in the bit size of P as soon as delta, is smaller than P power to this fraction. But the interesting question is that by computing a closest vector of a lattice of dimension 3 times k minus 1. Well, let me to explain you what's the meaning here of heuristic, and also which is the meaning of the heuristical meaning in the case of using the Coppersmith method. I mean, here, I mean, the heuristic in the theorem, the heuristical, the Gaussian heuristical is said that, well, it's unlikely to have two vectors linearly independent vector of node smaller than the volume power 1 over the dimension. This is the Gauss heuristical. This is basically due to the Hadamard inequality. But there's another method, also, better, introduced, given, by the same author that I commented before. In this case, delta should be smaller than this, than this one. Okay, so this one is better than this one because this one is bigger. This is 3 over 11. Is bigger than 1 over 4. However, the lattice that it requires is a huge lattice. I mean, huge lattice in the sense that, the dimension of the lattice in the sense that you cannot able, that does not make sense for practical application. The heuristical method here in the Coppersmith method is as follows. You have an ideal, a polynomial ideal, and then you introduce new polynomials, and you hope that the new polynomials, that the variety of the idea of this new ideal is a zero-dimensional ideal. That is, the variety has a finite number of points. Of course, it's quite natural. Definitely, it's quite natural. But it cannot be proven in some of the cases. So it's heuristical. And also, it's forgiven. I mean, you cannot use it in practice. This theorem, in the case that you only have 3 approximations to 3 consecutive values of our elliptic car produced by the elliptic from the elliptic generator, and we get, we can get, deterministic polynomial time, because this is heuristical, not only because, with fixed k, also you can get, I'm not able to prove, for fixed k, a polynomial time, deterministic polynomial time algorithm, because to bound the back side contain a lot of equations, very difficult equations, and that's the reason that we cannot get,
I'm sorry, you have 1 minute.
Oh, okay. So, thank you. So in that case, let me just to illustrate it, or you only have 1 minute. Let me to illustrate it finally my implementation. That or just a couple of comments, about the implementation that I have done. I think that they need to share also this. To share this. Let me say here. Okay. Anyway, let me comment again. Let me say that we have implemented in SageMath both methods. Okay, and both methods match our threshold. But no, we can check, for small primes. I would say, for 1,000 bits. Yeah, it's the match, the bound. The threshold. That's the reason that we think that this is quite natural. Okay, so thank you very much for listening to me, and I'm here if you want to ask me a question. I finished.
Thank you very much.
Thank you.
Are there any questions or comments? Yes.
Could you please compare the implementation of your algorithms with the other existing solutions?
Well, basically, you are talking about implementation or just theoretically?
Well, the algorithms and possibly the implementation and also the other existing software which allows one to solve similar problems.
Well, in fact, I told you, I mean, the technique using those Coppersmith method, I mean, you cannot implement in practice because the huge lattice dimension, and it's required to compute the Lenstra over Lenstra basis, you know, for, you know, I don't know, I mean, for instance, in the previous case, you know, 100, I mean, the dimension of lattice is 102. And just to obtain, say, a strong result or valid results, the size of the prime should be bigger. I mean, something like 2,000 bits. There is no way, I mean, to do that.
No, just no way, I see.
From the implementation point of view, from the theoretical point of view, it's clear. I mean, this bound is better than this bound, obviously. But this is heuristical, okay? Also this is heuristical. But I mean, with fixed k, for instance, you know, k, you know, 3, as I told you, you have, you know, a lattice dimension, the lattice dimension is 8. Here, the lattice dimension, we don't know the lattice dimension, in fact, because the number of monomials, the number of polynomials that they require, and then the number of monomial is huge.
Okay, I see. Thank you very much.
You're welcome.
Are there any further questions or comments? No questions. Then let us thank the speaker once more for his very interesting talk.
Thank you.
is entitled On the Complexity and Parallel Implementation of Hensel's Lemma and Weierstrass Preparation. The authors Alexander Brandt and Marc Moreno Maza. Unfortunately, I'm sorry, I do not know who is the speaker. Yes, we can see you. Please switch to your talk, and you can start your talk. Are you a speaker? Okay. Can you please enlarge to a full screen? Okay.
Perfect. Okay, so I want to start with just a little advertisement on the new journal, Maple Transactions, if you have not heard about it yet. It's an open access, free, essentially, journal, looking for all topics of interest to the Maple community, computer-assisted mathematics, education, and so forth. So you can look for more information at mapletransactions.org. All right, so hello everyone. My name
Excuse
is
me, Mark.
Brandt.
Excuse me, it's very difficult to hear you. Maybe you could increase the volume somehow, or
Alex, can you increase your volume?
Yes, yes, that's much better.
Okay, is that better?
Yes, yes, excellent. Thanks.
Excellent. Okay. So hello everyone, my name is Alex Brandt, and today I'm speaking on the complexity and parallel implementation of Hensel's lemma and Weierstrass preparation. This is joint work with Marc Moreno Maza. What we call Hensel factorization, or factorization via Hensel's lemma, is one method for finding the roots of a multivariate polynomial with respect to one of its variables. In the bivariate case, the well-known Newton-Puiseux method computes Puiseux series to describe the roots. The Hensel-Sasaki construction, also known as EHC, provides a method to describe the roots as multivariate Puiseux series. When the polynomial, whose roots are to be computed, is monic, EHC reduces to our so-called Hensel factorization and produces multivariate power series rather than Puiseux series. This problem has many applications, such as in computing the limits of rational functions, computing limit points and topological closures, or even as a practical variant of the Abbe-Yonkar-Young theorem. The ultimate goal in this research is to obtain a practically efficient implementation of Hensel-Sasaki construction to support those applications. Toward that end, we consider in this work efficiency of the more simple Hensel factorization. In previous work, we've examined the practical efficiency of multivariate polynomial arithmetic presented at CASC 2018. And this polynomial arithmetic underlies our lazy power series implementation, which we presented at CASC 2020. In that work, we discussed serial implementations of lazy Weierstrass preparation and lazy Hensel factorization. That is to say, power series based on lazy evaluation techniques. In that work, we showed that the practical performance of this scheme greatly improved upon the available implementations in Maple and Sage for multivariate power series. Now we will further extend the efficiency of our Hensel factorization by formulating and implementing parallel algorithms for it. Specifically, we'll present the following details: the complexity of our lazy evaluation scheme for Weierstrass and Hensel, parallel algorithms for both those algorithms as well, and the composition of parallel schemes, and in particular, the parallel Weierstrass preparation within Hensel factorization. We will apply these complexity estimates to dynamically load balance the composition, and then we will discuss our parallel performance and experimental results. Our plan is as follows. First, some notations and background. Then we'll discuss lazy Weierstrass preparation, its complexity, and a parallel algorithm. Then we present the same for Hensel factorization. Finally, the parallel performance of these methods is evaluated in our experimentation. Let A be the ring of multivariate power series over an algebraically closed field. Denote by M its maximal ideal. We write an element of this ring F as a summation of coefficients and monomials, where x to the e represents a multivariate monomial. F subscript k denotes the kth homogeneous part of F, that is, all terms of total degree k. Notice that the kth homogeneous part belongs to the maximal ideal raised to the kth power minus the maximal ideal raised to the kth plus 1 power. With a new variable y, we create a polynomial ring with multivariate power series coefficients. We call elements of this ring UPOPs, or univariate polynomial with the power series.
Alex, your volume went down.
Okay. Thank you. Weird. Okay, better again, hopefully. All right, denote by deg the degree of the u-pops in its polynomial variable. Power series based on lazy evaluation.
No, it's going down again.
Sorry for the difficulties, everyone. Okay, well, it's back up. Weird. So lazy power series is one where we compute terms on demand without requiring computation to start again from the beginning. The precision of a power series is the degree up to which terms of the power series have so far been computed. In our lazy evaluation scheme, a power series is stored as a collection of terms up to that precision, along with an update function, which is used to compute terms of higher precision as necessary. Such update functions often require parameters to compute terms of the requested degree. For example, in addition or multiplication, the two power series being added or multiplied together must be passed to the update function. Thus, our lazy power series captures such parameters to effectively create a closure for the update function. When such parameters are themselves power series, as in the case of addition or multiplication, we say that those power series are the ancestors of the power series being computed. As an example, we can consider this ancestry tree implicitly created through lazy power series arithmetic. To compute the power series P, which is f times g plus a times b, the intermediate products h and c are lazily computed, and then the sum of p computed from those products. In this scheme, when a user or subroutine requests terms of higher precision for p, then the algorithms automatically traverse up the ancestry tree to update h, f, g, a, or b as needed.
Went down again.
Before finally computing the sum terms of p. Okay. Hopefully that's better. Okay, so now that we have lazy power series defined, we can talk about Weierstrass preparation and its lazy implementation. We begin with a theorem stating Weierstrass preparation in the context of u-pops. Let f be a u-pops of degree d plus m, where d is the smallest
Down again.
such that there you go. D is the smallest integer such that AD, the coefficient, is a unit in the power series ring. Then, as long as f does not reduce to 0 modulo the maximal ideal, f factorizes into two u-pops, p and alpha. Alpha is of degree m, an invertible when viewed as a power series in Y, and p is a Weierstrass polynomial. That is to say, it is monic, and all its other coefficients belong to the maximal ideal. Our complexity estimates for lazy Weierstrass preparation show that in the case of two variables, computing p and alpha up to precision k can be done within d times m plus 1 times k squared plus dmk operations in the base field. The details of that complexity estimate are in our proceedings paper. Now we'll see how to actually compute Weierstrass preparation lazily. Let f have coefficients al, p have coefficients bj, and alpha rather have coefficients ci. If we equate individual coefficients in the polynomial equation f equals p alpha, we obtain these d plus m plus 1 equations. These equations follow two patterns. The upper d equations, the upper triangular portion, consists only of products of b's and c's. Meanwhile, the lower m plus 1 equations, the lower triangular portion, also contain a lone c of I term. Our goal is to solve these equations modulo successive powers of the maximal ideal. That is to say, computing terms of increasing precision. Modulo the maximal ideal, the coefficients of p reduce to 0 by definition. Then the lower triangular portion of these equations simplifies greatly to tell us that each coefficient of alpha, ci, is equivalent to a d plus I modulo m. Then we will update p and alpha in two phases. Phase 1, we update p, and then in phase 2, we update alpha, going back and forth to update them simultaneously. In the first phase, we update p using that upper triangle of equations. Here, we've rearranged those equations so that each one has a unique bj on the right-hand side. Since alpha is invertible, that means C0 is also invertible as a power series, and thus we can perform power series division to solve for b of 0, say a of 0 divided by c of 0. We can also let capital Fj equal the entire left-hand side for each of these j equations. Then Fj divided by C0 gives us the formula for B of j. Notice that there's a sequential relation in these equations. We first have to update B0 in the first equation before we can use it to update, say, F1 or this formula A1 minus B0 C1 in the second formula. And then using B1, put it into the third equation, and so on. Nonetheless, with our lazy power series arithmetic, this updating of the Fj's and the Bj's through power series division is automatically performed lazily thanks to our ancestry trees. In phase 2, where we update alpha, the process is very similar, where we rearrange those remaining equations so that the lone C of I term is on the left-hand side, and then the right-hand side represents the simple power series arithmetic that we can follow to update those C of I. Here, notice that unlike in phase 1, there's not a linear dependence on each equation. These power series can actually all be updated simultaneously. For example, consider that we want to compute the kth homogeneous part of C of m minus 1. One would expect that we need to have the kth homogeneous part of C of m available as well for this linear dependence. However, the corresponding 0th homogeneous part of B of d minus 1 that's needed for this product is 0 by definition. And so there actually is no dependency when computing the kth homogeneous part between all of these equations. So we can update all of these C of I simultaneously, which of course will help in our parallel implementation. So speaking of those parallel opportunities in Weierstrass, these opportunities are based on the famous MapReduce pattern. In phase 1, the summations for computing the homogeneous part of a power series product can be computed using MapReduce. That is the products implicit in the formulas for Fj and the summation within the power series division for computing Bj. In particular, the MapReduce pattern sees that different threads compute different indices of the summation, and then the reduce step efficiently combines partial sums into a single sum. For example, in this formula, a first thread might compute indices I equal 1, 2, 3, 4, and a second thread may compute indices I equal 5, 6, 7, 8. In phase 2, we can, of course, update all of those C of I independently and simultaneously with a simple map step. However, we can also use MapReduce within the update of each individual C of I for those power series products, just as in phase 1. Notice that where the Bj's and the C of I's are power series and are in fact multivariate power series, they require different amounts of work to multiply depending on the index of the homogeneous part. For example, multiplying the first homogeneous part of B of j by the k minus 1 homogeneous part of C0 is much less work because Bj of 1 is very few terms compared to a more square product for the k over 2 homogeneous part of B of j times k minus k over 2 homogeneous part of C0. We'll discuss that difficulty later in our experimental results. Considering other parallel challenges to load balancing in a parallel implementation, consider again phase 2, where we update alpha. In these n+1 formulas, all of the variables are in fact full power series, and so each multiplication requires a substantial amount of work. And if we notice, the number of products in each equation is not well balanced. So the work between each equation is not well balanced, and a simple map over updating each CI would not be very good for parallel speedup. Instead, we like to assign threads to update maybe multiple equations so that the total number of power series products computed by each thread is roughly the same. For example, one thread might compute and update C of m minus 1, and C of m minus 2 for a total of 3 power series products. And then a second thread might update C of m minus 3, which itself contains 3 power series products. Before considering the parallel performance of that scheme, let's now apply it within a parallel Hensel factorization. Theorem 3 presents Hensel's lemma for UPOPs. Let F be a monic UPOPs of degree D, and denote by F bar all the power series variables of F evaluated to 0. F bar then has R roots, say C1 through CR, with respective multiplicities D1 through DR. Then Hensel's lemma tells us that there exists a factorization of F into R factors, such that each factor has a corresponding root CI and a corresponding degree DI. The proof is straightforward and constructive, directly leading to a serial algorithm that we implemented and presented at CASC 2020. First, one applies a linear change in coordinates, sending CR to the origin. Call this shifted UPOPs G. Then by construction, G satisfies the conditions of Weierstrass preparation to factorize as P and alpha, with P of degree dr and alpha of degree d minus dr. Reversing the shift, we obtain the factor FR from P, and reversing the shift on alpha, call this new UPOPs F hat. Then we can proceed recursively or iteratively on F hat to shift a different root to the origin and apply Weierstrass preparation again. Repeating for all roots, we obtain all the factors, and so inductively the proof is complete. We could present an algorithm, but for the sake of time, I will skip that. It follows directly from the proof. Considering now the complexity of Hensel, let di hat be the degree of fi hat. That is, the degree of the polynomial which is input to Weierstrass at step I. The input polynomial is, of course, then f1 hat. At each iteration, we have to do a shift of degree di hat, a Weierstrass preparation, producing p of degree di and alpha of degree di hat minus di, or simply di plus 1 hat. A shift of degree di to obtain fi from p, and then a shift of degree di plus 1 hat to obtain the next polynomial for the next iteration from alpha. Putting this all together, we arrive at theorem 4, which states the complexity of the Hensel factorization algorithm. In the case of two variables, for an input UPOPs of degree d, updating all factors to precision k requires the big O of d cubed k plus d squared k squared operations in the base field. We can compare our complexity results to other works. Here, let's just denote dy as the degree of the input UPOPs in its polynomial variable, and let d be the total degree. Denote by mn a polynomial multiplication time. Then factorizing f by our method requires dy cubed k plus dy squared k squared operations. Meanwhile, the Hensel-Sasaki construction requires d cubed md plus k squared dmd operations. Over the complex numbers, Kung and Traub show that the Newton-Puiseux method can be done in d squared mk operations, and Chanovsky and Chanovsky lower this bound to d squared k. The method of Berthemieux, Le Cerf, and Contant, also based on Hensel lifting, performs in mdy, log dy, k, and k. If we consider the cost of the initial root finding step, say as Rn, then our complexity estimate simply adds a lower ordered term to the big O notation, which would simply be hidden once we increase the value of k. Comparatively, the method of Neger, Rosenfield, and Trost has a k times Rdy factor in its soft O complexity. These comparisons show that our method is already an improvement on the Hensel-Sasaki construction by a factor of log d. On the other hand, we can consider the practical performance as well. This experimentation was shown originally at CASC 2020, which shows that our blue implementation BPAS outperforms that of the Hensel-Sasaki construction, shown in green, by orders of magnitude. Transitively, previous work by my co-author shows that the Hensel-Sasaki construction significantly outperforms Kung and Traub's method in practice, despite the latter's much lower complexity. This is in fact quite promising, since it highlights that a lower complexity does not immediately lead to better practical performance. To that end, we can consider the practical performance of Hensel with our applying parallelization. One may think that the successive and iterative nature of our algorithm for Hensel factorization would form dependencies not conducive to concurrency. However, our key observation is that through the ancestry tree and lazy evaluation, the successive shifts in Weierstrass preparations create a pipeline. For example, in this ancestry tree, we could see that we could update, or rather once the first factor is updated to precision k, then P1 and alpha 1 are also updated to precision k. Therefore, we can start the work to update the second factor to precision k as well. Meanwhile, simultaneously, we could continue the updating of F1, P1, alpha 1, G1 to precision k plus 1. This pattern continues for all the factors and all increases in precision, leading to a classical pipeline pattern. An important consideration, though, is that the work required for each stage diminishes along the pipeline, as degrees are continuously reduced by those successive Weierstrass preparations. Since Weierstrass is the majority of the cost for each factor, our proposed pipeline then looks to compose parallel patterns and use parallel processing for Weierstrass within each pipeline stage. Then, by supplying more threads to the earlier stages, so to the earlier factors, we can attempt to make the actual runtime of each stage roughly equal. From our complexity estimates, we know that the work in Weierstrass scales as the product of the degrees of P and alpha. With our notation used in Hensel, then, we want to assign a number of threads Ti to the stage I, so that Di times Di plus 1 hat times K squared, Di plus 1 hat divided by Ti is equal for each stage. So that is to say, the product of P and alpha divided by the number of threads computing that Weierstrass preparation is roughly equal. An even better solution then would be to assign multiple threads to update, or sorry, one thread to update multiple factors. For example, one could assign 3 threads to update the first factor, this blue region, 2 threads to update the second factor, this red region, and then 1 thread to update both the third and fourth factors, the green and purple regions. A little bit of profiling data shows this diminishing of work. In our serial implementation, updating the first factor for this Hensel factorization took the majority of the time, and then time diminished very quickly for each factor. Using our complexity estimates, we could assign and distribute threads across those individual factors, say 6, 4, 1, and 1 for a total of 12 threads. However, doing so, presents relatively good parallel speedup, yet the latter stages are still waiting for a long time for the data to be available from the first stage. So one could then consider an alternative distribution of threads based on the fact that if we had the actual serial runtimes for each stage, we could better distribute the threads. Using that serial runtime information, a better distribution of threads is, say, 7, 3, 0, 2, with the third and fourth factors being updated in the same pipeline stage. This provides better load balancing and better parallel performance. In practice, one could obtain this serial runtime for, say, some value of k, and use that to distribute the threads for a parallel execution with a large value of k. Here we have some pseudocode describing the creation of the pipeline, but I will skip that for the sake of time and go straight to the experimentation. Looking first at Weierstrass preparation, here we consider a family of polynomials which create a p of degree 2 and an alpha of degree r minus 2. Our implementation achieved pretty good parallel speedup, up to 9 times on 12 cores. The general trends are that with higher degrees of the input polynomial, parallel speedup increases, and secondly, parallel speedup increases when more threads are used. That is to say, our method scales well. On the other hand, we can consider a Weierstrass preparation producing p and alpha of equal degrees. In this case, parallel speedup is not as good, but still 7 times on 12 cores. This diminished performance can be attributed to the fact that p has a larger influence on the overall computation. And as we know, when we have multivariate power series being multiplied together, the MapReduce is not as efficient as it could be, leading to unbalanced work. And here we need to have better load balancing in future works. Moving to Hensel factorization now, we can consider again our previous example. And here, the input upops is in 2 variables. In this case, speedup is quite well, reaching almost 9 times again on 12 cores. Here, the solid lines represent a complexity-based distribution of threads. Meanwhile, the dashed lines represent distribution of threads based on our serial runtime estimates. What's interesting is that as degrees increase, the complexity estimate distribution and the serial runtime distribution of threads is roughly equal, which says our complexity estimates are quite good in this dynamic load balancing. In another example, this is the multivariate case. Again, we see that parallel speedup is still kind of good, but a little bit lower. Again, because of that load balancing in multivariate power series or multiplication. So to conclude, we've seen complexity estimates and parallel algorithms for lazy Weierstrass, lazy Hensel factorization, and the composition of parallel patterns to provide good parallel performance and dynamic load balancing. In future, we have to look better at the multivariate case and to better distribute the work. And finally, we should also consider reducing the overall complexity, say, by the use of relaxed algorithms in the Weierstrass preparation. All right, and that concludes my talk. Thank you. Was there any questions?
Thank you very much. Are there any questions or comments? Then I have a question, and you maybe think about next question. My question is as follows. You have mentioned several times during your talk that at different stages of your parallel algorithms, unfortunately, the work amount changes, the work amount which should be done by each separate processor. But there is a wish to distribute this work uniformly among the processor so that the idle times be minimal.
Yes.
Have you used maybe some special algorithm, computer algorithm, for the approximate redistribution of this work between the processors? How did you redistribute the work?
So mostly the actual distribution of work to processors is left alone to the operating system to choose how to do that mapping from threads to actual CPU cores. But when we did, say, profiling to say, how do we distribute the number of threads to our individual stages, say, for updating each individual factor. Of course, first we used our complexity estimates, which suggest that we should distribute threads so that this ratio, the product of the P and alpha divided by the number of threads we give to that Weierstrass preparation, is roughly equal as degrees reduce throughout the pipeline. And so that number of threads, Ti, is scaled. You can see here, if we consider this, these factors, the product of the degrees for the first factor is 3, 2, and 1. So that means we should give 3 times as many threads to factor 1, twice as many threads to factor 2, and 1 thread to factor 3.
Thank you. Have you maybe an intention to include your parallelized versions of your algorithm in the, for example, parallel version of Mathematica or Maple?
So these algorithms are implemented and available in the BPass library, and that's already open source. So these algorithms are available to download and play with at your leisure.
Thanks. Just a moment.
Well, basically, I have the same question that I asked yesterday after a topic on related issues. And with this, is it possible to somehow adopt this approach and use it in the case of analytic functions rather than polynomials? Because as we know, the Weierstrass preparation theorem is just a step towards the general Weierstrass decomposition of an analytic function with a given divisors into a product, the Weierstrass product. So is there any hope to move it, to lift it up into the analytic category?
I think that that generalization is certainly possible. The implementation would be more challenging for sure, but with some, enough work and attention, then I think it's very reasonable to think that this approach can be extended.
Yes, but that's not done yet by anyone. Right?
No, not that I know of.
Yes, thank you very much.
Are there any further questions or comments? No questions. Then Thank you once more very much for your very interesting talk.
Thank you.
And now we must proceed to the next talk of this session. The talk is entitled Computational Schemes for Subresultant Chains. The authors Mohammadali Asadi, Alexander Brandt, and Marc Moreno Maza. Here is the speaker, Alex Brandt. Please.
Hello, everyone. The speaker of this talk is Ali Asadi, and that's been a teamwork of Alex and Ali under the supervision of Professor Marc Moreno Maza at the University of Western Ontario. And today I'm going to talk about computational schemes for subresultant chains. Speaking of polynomial system solving, the theory of regular chains extends the characteristic set method both in terms of computational efficiency and theoretical model. Here in this code listing, we take advantage of the triangularized method in the regular chains library in Maple to solve the system of polynomial f. This triangularized method is utilizing a variety of subroutines, including but not limited to subresultant chain, regular GCD, factorization, and so on, to compute some systems known as regular chains. To see the importance of subresultant chain within this solver, consider the following system where x is the variable, the unknown, and a, b, c, and d are parameters here. We start with computing the remainder, of course, that the first remainder of R3 and R2 is going to be R1 using the Euclidean algorithm. And as R1 has degree 1, so it's sort of impossible for R3 and R2 to have exactly two common solutions. Next, we also observe that for with respect looking at R1, there are two cases for a minus t, the coefficient of x. A could equal to c, and a is not equal to c. There are two cases basically. For the first one, basically two subcases arise, like when this constant part b minus d equals 0, and when b minus d doesn't equal 0. So for the first subcase, R3 and R2 become sort of identical. Thus, they have three common roots. Otherwise, they don't have any common root. For the other case, when a isn't equal to c, we can continue using Euclidean algorithm to calculate the next remainder, which is denoted as R0. And that is this giant fraction based on the parameters a, b, c, and d. So if these parameters are so that R0 becomes 0, then R3 and R2 have exactly one common root. Otherwise, there isn't any common root. We can follow the same strategy with more complex problems. However, various computational issues, such as the size of coefficients of remainders and the number of cases to be considered, would grow rapidly. We have to deal with like these sort of computational issues. But we're lucky, as the theory of subresultants deal with these computational issues. An informal definition for subresultant chain that would be for two input polynomials with the same main variable x. The theory of subresultants produces a sequence of polynomials S0, S1, S2 known as subresultants that have some specifications, such as sk is either 0 or has a degree in x less or equal to k. For two successive subresultants, sk and sk plus 1, if they are non-zero, then we have the degree of sk is less than or equal to degree of sk plus 1. And one important specification is that each non-zero remainder of input polynomials from the sequence of remainders calculated by Euclidean algorithm is proportional to a non-zero polynomial sk. So in the following example, R3 to R1 presents the sequence of remainders, and this subresultant chains are represented as S3, S2, S1, and S0. And you see that proportional relation between subresultants and remainders, and the fact that and you see the difference between the size of coefficients and the fact that the coefficients of subresultants belong to the same ring of coefficients of input polynomials. But in practice, for some examples, the whole sequence of subresultants may not be needed. For example, for f and g, these are like two bivariate polynomial systems. These two bivariate polynomials, we only need the last two subresultants, S0 and S1, to solve f equals g equals 0 from the list of entire subresultant that is S5 to S0. That is yielding the so-called speculative approach, which is one of the main objectives of this talk. Here, within this talk, we are focused on subresultant schemes in support of the triangularized algorithm and developing the DPass library, that is C++ library that's open source. And the main achievements would be like developing fast basic arithmetic for univariate and bivariate polynomials with, or prime fields, developing modular subresultant chain schemes for univariate and bivariate polynomials over arbitrarily precision integers, designing and developing speculative subresultant schemes for univariate and bivariate polynomials, and developing a cache-friendly version of the Duco subresultant chain algorithm for multivariate polynomials. To continue, we'll review the theory of subresultant chain, and we'll talk about a modular and speculative subresultant scheme, and we'll switch gear and talk about, for multivariate polynomials, we'll talk about cache-friendly approach implementation for Duco, the famous Duco subresultant chain algorithm. And we'll wrap up our talk with conclusion and future work. So here, consider B as a commutative ring containing unity. We define polynomials A and B as follows. And here, for B as a field, we definitely can define a GCD, and the sequence of remainders will be presented as R0, R2, R0, R1, R2 to RL, when basically RL is a GCD. And the sequence of quotients, the corresponding sequence of quotients defined as Q1, Q2 to QL, and we also can represent the quotients within the quotient matrices as follows to get this separated relation between like to compute two successive remainders from the multiplying of quotient matrices. The sequential matrix of A and B is basically the square matrix of coefficients of input polynomials. The determinant of this matrix is the so-called resultant, and the relation between resultant and GCD is that, like, let's be consider B as a UFD. The GCD of two input polynomials A and B is a non-constant polynomial if and only if the resultant is 0. A refinement of the resultant would let us compute the so-called subresultant chain by keeping track of the sequence of remainders to compute like this sequence of subresultants, and that is basically an adapted version of the fundamental theorem on subresultants. And like as we saw in previous slides, these are like showing the proportional relation between the subresultants and the remainders. To define subresultants, to define a formal version of subresultants, we need to define the determinant of polynomial of matrix M, that is basically a polynomial where the coefficients are the determinant of some sub-matrices. And the K-subresultant of two polynomials A and B is defined as the determinant of polynomial of a matrix, sort of a sub-matrix of the coefficients of input polynomials. And the specialization property of subresultants says that, like, consider A and B as two commutative rings with identity, psi be a ring a homomorphism from B to A, such that we have psi of leading coefficient of A and psi of leading coefficient of B non-zero. Then for every k, we have the k subresultant of psi A and psi B equals the psi of the k subresultant of A and B. To talk more about the important properties of subresultants, S0 is a resultant within the subresultant chain. If Sk is non-zero, then its degree is at most k. If Sk, the k subresultant, has degree k, then we call it a non-defective or regular subresultant. Otherwise, we call it defective subresultant. And for convenience, we extend the definition of the subresultant chain to the n subresultant as follows. And the relation between subresultants and GCDs is that, like, for, let's say, B as U of t, for two polynomials A and B over B of y, if for some k, we can find subresultants such as k, so that this is non-zero, but all the Si other subresultants with less degree and then k is 0, then there exists coefficients alpha and beta, so that alpha times GCD equals beta times the k subresultant of input polynomials. That's the relation between GCDs and subresultants. An algorithm to compute the entire subresultant chain utilize the divisibility relation of a subresultant that is also known as the Brown's algorithm. And the well-known optimization for this algorithm is a so-called Duco subresultant chain that computes the entire non-zero subresultants of polynomials over a commutative ring. To compute subresultants using modular methods for polynomial univariate and bivariate polynomials over arbitrarily precision integers efficiently, we take advantage of fast basic arithmetic over prime fields, heuristic CRT algorithm, and evaluation interpolation techniques. Here, for univariate polynomials over prime fields, these polynomials are stored in a dense representation where coefficients are in Montgomery form to take advantage of fast division and multiplication over prime fields. Multiplication dynamically chooses between plain, Karpov, and FFT-based multiplication. Division dynamically chooses between Euclidean algorithm and fast division algorithm. That basically the fast by fast algorithm for division, we mean that is an optimized power series inversion scheme that is firstly implemented in algebra using FFT and real product 3. And GCD dynamically chooses between the classical extended Euclidean algorithm and the one based on half GCD. So comparing multiplication and division algorithms for univariate over polynomials over prime fields, here these plots are in log scale. There are logarithm seconds over degrees of polynomials. The left one represents the comparison between our plane, Karpov, FFT, and BPass against the fast multiplication algorithm in the Hensel library. And with having a fast division, with having a fast multiplication algorithm, the right plot shows the comparison between the division algorithms, and you see that, like, utilizing the FFT-based multiplication, how our division algorithm is slightly faster than the NTL library. For implementing the GCD or of univariate polynomials over prime fields, we utilize the half GCD algorithm, also known as fast extended Euclidean algorithm. And that this algorithm can be interpreted as a divide and conquer and asymptotically fast technique to compute the GCD through calculating the quotient matrices. Or so that, like, with this matrix times vector multiplication, we have all of a sudden the GCD. And with following the implementation in the Intel library to implement, like, these algorithms in BPass, we've got same performance for our GCD algorithm. To compute the entire subresultant chains of polynomials in univariate and bivariate, basically univariate and bivariate polynomials or integers, we proceed as follows. For univariate polynomials over prime fields, their subresultant chain is essentially obtained by an optimized fraction-free version of the Euclidean algorithm. That is indeed an adaptation of the factorization theorem on subresultants. For univariate polynomials over integers, their subresultant chain is obtained by reducing to the previous case via a so-called probabilistic CRT algorithm. For bivariate polynomials over prime fields, their subresultant chain is obtained by reducing to the first case via evaluation interpolation techniques that are powered by FFT when possible, otherwise by Lagrange's method. And for bivariate polynomials or integers, their subresultant chain is obtained by reducing to the previous case via the CRT algorithm. In the system solver, there are usually only a few subresultants starting from S0, S1 are needed, as we saw in one example, which this can be seen as a consequence of the celebrated shape lemma. This suggests to compute the subresultant chain speculatively, taking advantage of half GCD that is desirable to compute subresultants of index 0 and 1, delaying the computation of subresultants of higher index until proven necessary. So we utilize using the half GCD to compute subresultants speculatively, and to the best of our knowledge, there is no successive implementation of this idea in the literature. So Richard proposes a fraction-free adaptation of half GCD, and then Lichteg and Owa propose a divide and conquer algorithm for computing subresultant chains, and Losov introduced the extensions and the complexity analysis of this algorithm. However, without any speedup, he couldn't beat the Duco and modular schemes with his new algorithm. For a non-negative integer k, Gartner and Gerhard introduced a half-GCD algorithm that computes the quotients q1 to qhk, where hk is defined as follows, and we extended their algorithm to compute any two successive subresultants within the entire subresultant chain, utilizing an adapted version of this half-GCD algorithm. Our adapted half-GCD algorithm provides a mechanism to compute only two successive subresultants without computing others in the chain, a so-called speculative computation. And we also store cache, or let's say cache the intermediate data and utilize to calculate higher subresultants in the chain without calling half-GCD again. The use of a speculative scheme for polynomials in ZP of Y, along with the evaluation interpolation technique and CRT algorithm, use speculative schemes for univariate and bivariate polynomials over arbitrarily precision integers. So the left plot here shows the performance of subresultant chain algorithms based on modular methods, comparing with the Duco algorithm, and you see that we've got up to 400x speed up using these subresultant chain based on fast modular methods. And the right-hand side 3D plot compares the subresultant chain based on modular methods and the speculative subresultant when we only compute S0 and S1 utilizing half GCD. And you see that we also get some significant speed up using speculative approaches instead of only using fast modular methods to compute subresultant chains. So here, the integration of our subresultant schemes into the multi-threaded BPass solver, we've got up to 4x speed up for solving some well-known, hard, difficult to solve bivariate systems in literature. And now let's switch gear and talk about subresultant schemes for multivariate polynomials. Like subresultant schemes for multivariate polynomials, they're basically in almost all computer algebra softwares, including but not limited to the regular chains library in Maple and the algebraics library in Mathematics. And they all have an optimized version of Duco algorithm. But what is Duco? As we reviewed, the first algorithm to compute all subresultants in a way similar, but fraction-free to the Euclidean algorithm is known as the Brown's algorithm, and Duco algorithm is an optimized version of that Brandt's algorithm. So the following theorem shows the main parts of this algorithm. Lazarus proved an optimization to compute the first equation that is known as Lazarus optimization, and the Duco proved a further optimization in order to compute the second equation that is also known as Duco optimization. We further optimized Duco optimization, that is this algorithm on the left-hand side, to make better use of memory resources through in-place arithmetic and refinement of intermediate calculation. This subresultant chain is the so-called cache-friendly Duco algorithm, and this is denoted as opt-Duco. So the comparison between the Duco implementations in Maple and BPAS, where Maple is using around 32 gigabytes of memory to compute the entire subresultant chains of two input polynomials. The original implementation of the Duco algorithm in BPAS is using only around 9 gigabytes, and our cache-friendly Duco algorithm is only using around 3 gigabytes of memory. So in this talk, we have discussed efficient speculative and cache-friendly schemes for computing subresultants in support of the multi-threaded BPAS polynomial system solver, a triangularized algorithm. We designed speculative scheme, and these speculative schemes yield speed-off factor of 7x and 2x for polynomials in z, y, and z, x, and y, respectively. And to develop these speculative strategies for univariate and bivariate polynomials, we extended the half-GCD algorithm. That is the work of Gaetan and Gerhardt. The subresultant schemes based on fast arithmetic are up to 10x and 400x faster than non-modular schemes. And Duco algorithm for polynomials, for univariate and bivariate polynomials. And we also further optimized a well-studied scheme known as Duco subresultant chain algorithm. And our cache-friendly Duco algorithm is at least 2x faster than the implementation of Duco algorithm in Maple. And regarding the memory usage, this is 3.2 and 11.7x, using less memory than our implementation of the original Duco algorithm in BPAS and the Duco implementation in Maple. As part of the future work, one can exploit the parallel opportunities of the subresultant schemes based on evaluation interpolation techniques. For speculative schemes, one should study the theoretical considerations for when we can get the most benefit of using speculative approaches. One also can consider alternative ways to compute subresultants of multivariate polynomials such as Bezier matrices. And for polynomials with more than 2 number of variables but sparse, one should consider sparse evaluation interpolation techniques. These are main references that I use, and thank you for your listening.
Thank you very much. Any questions or comments, please?
Could you please show the first slides in your presentation with the initial system of equations that you would like to solve?
This one, you mean?
Yes, maybe. I mean, well, that's more like an example, but is there the general formulation of a system of algebraic equations that you aim at solving? Is it somewhere in the presentation?
Not really.
Not really.
Our algorithm.
Well, let's then look at the example on the next slide, please. On the second slide, yes. So you have 2 cubic equations in one variable with which are monic, and the other coefficients are symbolic and algebraically independent, right? Well, it's a bit difficult to see for us because those coefficients in the equations are exactly in the middle, where the 2 screens join. So you have x cubed plus ax plus b plus, and then x cubed plus cx plus d, and both are 0, right?
We are looking at them as a system of equations. Yeah.
Okay, yes. So, but still, so somehow, if you replace in the second equation x by another variable, say y, and look at the, well, even a more generic system of equations, if you have more monomials, just 2 equations in 2 variables, say, monic, and of the form that kind of is suggested by this example, and with all the other coefficients being algebraically independent and symbolic, well, any such system can be solved in a sense exactly by expanding the solution into a power series. So does this apply to the general case that you are looking at? Because I'm not sure if you have the very general system which you aim at solving in your presentation.
I would like to bring some comments here because I think there are maybe at least 3 questions.
At least 3.
Comments. So the first of all is that this example which is on the slide is just to show that the subresultant theory has the ability to encode a case discussion. So that was the only point of that example.
Okay.
Now the second comment is that the algorithms that Ali and Alex have implemented in the past, they can solve any input polynomial system. There is no assumptions. But one of the core algorithms in that machinery relies on the computation of these subresultant chains. Now for your question related to power series, yes, in fact, and that's implemented in Maple, we can also solve one-dimensional systems over a ring of power series. And that is related also to what Alex presented in the previous talk.
Okay, I see. Right. So, but still, the system that you are solving is completely general, just any system of algebraic equations.
Yes, completely general. So it will describe the roots in the algebraic closure of the field of coefficients of the input system. To be a little bit technical, this will describe the generic points of the prime components or reducible components in the sense of van der Waerden.
Okay, I see, yes. Thank you very much for that clarification.
In fact, regular chains were introduced by Michael Kalkbrenner to represent those generic points.
I see. Thanks a lot.
And the
very precise question. Thank you for all your entertaining questions during CASC.
Any further questions or comments? No question, no comments. Then thank you once more very much for your interesting talk.
Thanks.
Well, I actually have a question, if that's okay.
Sure.
Yeah, on slide number 15, if you can go there. I just wonder what is the middle product trick?
Okay, to compute, that's a very good question. To compute the power series inversion using sort of Newton's algorithm, if we wanted to use FFT, we can reduce the number of multiplications, sort of like in a divide and conquer manner. And that trick is known as middle product trick.
Oh, so FFT is the middle product trick.
So the middle product trick relies on FFT.
Relies on FFT.
So what is it?
Yes. So if you are using instead, let's say, Karpov multiplication, then the benefits will not be so great.
So that's not clear. So the middle product trick.
Middle product tricks relies on the FFT, and to get that to reduce the computation of the cost of multiplications, and for example, if you use Katsubo multiplication, you can get the benefit of using middle product trick, because you need a fast multiplication algorithm to get this nature of divide and conquer nature and to compute that power series inversion.
So to give maybe some complexity estimate, so maybe you know about the trick for doing fast division. So the fast Euclidean division of two polynomials. This can be done by reducing it to fast multiplication. If you do the analysis like it is done in the book Modern Computer Algebra, you will see essentially you need to do you can do your division at the price of 4 multiplications. But if you use middle product trick, the middle product trick, you can save 1. So instead of 4, you will pay 3.
So I know the FFT, but the middle product trick is kind of like like another version of the FFT or something.
No. It is really about the implementation of that fast division.
That fast division, yes.
Okay.
To reduce the cost of the number of multiplications that we need to compute that division.
Yes.
If you wanted to learn more, there is a very good paper of Flatte and Marc Moreno Maza naming implementation techniques for fast polynomial arithmetic in a high-level programming environment. They mean by Aldor, because this algorithm is originally implemented in Aldor, and also the code is available in the BPass library if you're going to go and look for more information about the implementation, the C implementation of this algorithm, and the theory behind it.
Yeah, thank you so much.
Thanks for your question.
And the idea is not from us, it's due from someone called Mulders.
Yeah.
All right. So any further questions, comments? Does anyone want to say something in auditorium or the online participants? Well, if not, then I would like to thank again everyone who's made it here. Thank you so much for attending. Thank you so much for being here. And of course, there's so much we can say to our online participants. We're happy that you could join us. And we hope very much that in a year from now in Turkey, in Gebze next year, all of us will meet, and hopefully many more people, for the CASC conference of 2022. So our program is finished. Unless there is anyone who wants to say something, I would like to officially declare this conference closed. Thanks for participating.
Maybe Timur.
Yes, sure. François?
Yeah.
Yes?
I would like at least to thank you for all this organization, because you did a really great job.
Well, actually, the head of the organizing committee is Vitaly Krasikov, who is here waving, but a bit difficult to see. So let's thank Vitaly. Yes, he's the main person in the organizing committee, and I was just helping out a little, just a little. So Vitaly, we appreciate your efforts so much. Thanks a lot.
Yes. Thanks. Thanks to all the participants and the in-person ones and those who participate online. I'm very glad that I managed to organize this conference this year, and I'm more than glad that the next year it would be some other people. Thank you.
Okay, so it's a bit sad, but we close now. So, bye, Marc, François. We'll stay in touch. Let's stay in touch, everyone.
Bye-bye.
And see you in Gebze next year.
Bye-bye. Yeah. See you in Gebze.
See you in Gebze.
Salut Marc.
À bientôt, François.
À bientôt.
J'imagine dans quelques jours pour discuter d'une autre conférence.
Allez, une à la fois.